Okay, so now we are going to look at the proof of correctness of the Kruskal's algorithm. So Kruskal's algorithm finds you the minimum spanning tree. We want to prove that it does find the minimum spanning tree for you. So to start with, let's say the tree that is found using Kruskal's algorithm is this tree T. It's just a spanning tree to start with. We want to prove that it is a minimal spanning tree, right? So we use the technique of proof by contradiction, where we will assume there is a hypothetical minimal spanning tree. This is typo here, is hypothetical. Okay. That there is a hypothetical minimal spanning tree, say T prime, okay, such that what the such that the weight of T prime is strictly less than the weight of T. Okay, so the weight of this hypothetical minimal spanning tree is strictly less than the weight of the tree, or the spanning tree, that the Kruskal's algorithm gives to us. Okay, we want to now argue whether such a situation is possible, whether such a hypothetical tree T prime can exist. Okay, so now if the weight of T prime has to be less than the weight of T, first of all, T prime and T have to be what? T prime and T have to be different trees. If they are the same tree, then then the weights will be the same, right? So T prime and T have to be different trees, which means there should be at least one edge difference. There should be at least one edge difference between the two trees. So what I mean by edge difference, there should be one edge, like an edge like E1 here in T, that is not in T prime, and to compensate for that, there should be some edge E prime that is in T prime that is not in T. So either way, it should be, there should be an edge here, not here, and likewise there should be an edge here, not here. So that's one edge difference. Another edge difference is there's an edge E2 here in T that is not in T prime, and there should be an equivalent edge E double prime, which means like corresponding to that or alternate E double prime that is in T prime and not in T. So in this case, in this example, we have two edge differences between the two trees. Okay, there are two edges which are here, not here. Likewise, there are two edges here that are not here, basically. Okay, so now what we will do is we'll pick an edge, this edge, say E1, that is in T and not in T prime. I'm going to put that edge in T prime. Okay, so if I put that edge in T prime, let me make it like this. Okay, it's going to create a cycle, right? So this is my E1. So if I put it in this T prime, it's going to create a cycle. Now all these four edges that are part of the cycle, cannot be in T, because if all these four edges from here to here to here to here, which are part of the cycle, are also in T, then T will have a cycle, but T is a tree, right? So which means there should be some edge in the cycle that is not in this tree, and we know that its edge is E prime, right? So which means we could now compare the weight of this edge E prime and E1. Okay, so how would you compare the weight of E prime and the weight of E1? Okay, now we can claim that the weight of E prime has to be what? Greater than or equal to the weight of E1. Because if weight of E prime was less than the weight of E1, the Kruskal's algorithm would have picked E prime to connect, and it would not have picked this edge, right? If E prime was less than the weight of E1, it would have picked the edge like this, okay, and not E1. But the fact that Kruskal's algorithm picked E1 or has E1 in it and does not have E prime in it indicates that the weight of E prime has to be at least the weight of E1, because Kruskal's algorithm considers edges in the increasing order of edge weights. So the fact that E prime is not there and you have E1 means the weight of E prime has to be greater than or equal to the weight of E1. So which means in this cycle we could as well remove this E prime and make E1 a permanent edge for this tree. Okay, we could make E1 a permanent edge for and make it a spanning tree. It's no longer a cycle. When we do that, what we are doing, the weight of T prime, it was something initially, the weight of T prime, right? It was something initially, and we removed what? The weight, removed edge E prime, and we added edge E1. So the overall weight, this is going to be less than or equal to the weight of the original initial weight of T prime. Why? Because this is, say, some value and you're subtracting, so let's pick up some numbers that's more easy to visualize. So the weight of T prime is, let's say, some 20, and I'm subtracting, say, the weight of E prime is, let's say, 5, and adding what? Weight E1, which is 3, because we know that the weight of E prime, say in this case 5, is greater than or equal to 3, right? It's actually greater than 3. So the net value, which is what? Which is 18, is less than the initial weight of T prime, which is 20. So by doing this, by removing E prime and adding E1 to the hypothetical minimal spanning tree, we are actually only reducing the weight of the tree, the spanning tree, even further, which means that tree T prime is not a minimal spanning tree to start with, because remember, a minimal spanning tree means the sum of the edge weights is a minimum, and we cannot find something better than or lower than that sum of the edge weights. Okay, so this is the best we can do, but we have now shown that we can even reduce the weight of the spanning tree, minimal spanning tree, which is not possible, right? So T prime is not a minimal spanning tree to start with, which is a contradiction. Now also you notice that by doing this kind of edge change, we are making T and T prime become more similar to each other. Initially they had two edge differences, now they have only one edge difference, which is this E2, which is here, not here, and E double prime, which is here, no longer here, is not here. So we can do a similar process of putting E2 here and removing E double prime, because the fact that E double prime is not here and E2 is here means, like this case, what? The weight of E double prime has to be greater than or equal to the weight of E2. Okay, so by doing the similar thing, we can get rid of this E double prime here and have E2 being part of this tree T prime. Okay, and now both the trees are the same, and when we do this edge change like we did earlier, the weight of T prime is even only going to reduce further if possible. It's not going to increase at all. So which means the weight of T prime approaches with every edge change and reduction and the corresponding reduction in what? The edge difference, because initially you have two edge differences. After doing one edge change, the edge difference reduces to 1. The weight of t prime is only reduces further, and eventually as t prime becomes the same as t, both have the same edge weight, right? Both will have the same edge weight. So if both have the same edge weight, then what's the case? The same total or total weight. So which means the weight of t prime to start with has to be only greater than or equal to the weight of t. But what was our initial assumption? The weight of t prime is strictly less than the weight of t, because with each edge change, what we are trying to do, we are trying to make t prime. So what we are not making, but we are trying to analyze and see the nature of the edges here, and we see that the way with every edge difference reduced between t and t prime, the weight of t prime is only going to reduce further if possible. It's not going to increase at all. So which means the weight of t prime eventually going to become equal to the weight of t, right? So, and with all those edge changes, it is going to only reduce. So when weight of t prime is going to become equal to the weight of t at the end, when it in the beginning, then it's going to be only greater than or equal to, because with each edge change, the weight of t prime was only reducing. From 20, it could have reduced to 18, and with this edge change, it could have reduced to 15, which is the weight of t, because after this edge change, they are the same, right? So which means to start with, the weight of t prime, which was 20, is greater than the weight of t, which say is 15, right? So but that contradicts to our original assumption that the weight of t prime is less than the weight of t. Okay, so which means we have now proved that there cannot be such a hypothetical minimal spanning tree t prime with the weight of t prime less than the weight of t. Okay, so we'll stop with this.